The third free response question on the mechanics practice test involved torques and rotation. This came up a little bit in the second problem, but this one is all dealing with torques and rotation. And the first part of it is looking at equilibrium, and then the last part of it is looking at the rod, and it's rotating around, and it looks at the idea of torque and angular acceleration. It's a fairly straightforward problem. It's one that if you understand rotation and if you understand how to do these types of things, should be one that you should be able to get 9 or 10 points on at least. That's above the average across the country on this problem, but this is definitely a problem that there are a lot of points available for you, and it's somewhat straightforward. So in this problem, you have a uniform rod. They give you the length of the rod and the mass of the rod. And at the left end, there's a vertical support on a frictionless hinge that allows the rod to swing up or down. And the right end is supported by a rope that gives you the angle of the rope. And then there's also a 0.5 kilogram block attached to the right end of the rod. So in part A, they ask you to draw and label vectors to represent all of the forces acting on the rod, and to show each force vector originating at its point of application. So on this rod, a good way to do this would be to sketch some things up top, so that way you know what to transfer down. Up top, if we look, we're going to have this weight of this 0.5 kilogram block. We also have the weight of the beam, or the horizontal rod. The weight of the horizontal rod acts at its center of mass, which is 0.3 meters from the end. You're going to have this rope pulling up at an angle, and then you have this hinge. And if you calculate this weight, the weight of the 0.5 kilogram block is 4.9 newtons. The weight of the 2 kilogram block is 19.6 newtons. And the vertical component of that tension is not going to add up to equal those two weights. That rope is going to be pulling up, and it's going to be pulling at an angle. It's going to be pulling horizontally. And that means that this hinge is also going to have to be pushing horizontally, and it's also going to have to be pulling up to help out the rope. The hinge and the rope together are going to have to add up to equal the weight of those blocks. That's something that we can look at a little bit later in the problem. But if you sketch your vectors on that one, make sure that you don't forget to transfer them down into the one that they gave you. But you can use that original diagram as a place to do some of your scratch work and to go through and do some of your calculations, draw some things, break some things into components, but on there you might have some extra stuff that you definitely don't want to include on your drawing in part A. There are points that you can lose if you include some wrong stuff, so you can put some stuff there and then go ahead and transfer it down. So for this, draw and label the vectors to represent all the forces. We have the weight of the 0.5 kilogram block, so it's the weight of the block. We have the weight of the rod. There's the tension in the rope. And there's the hinge that pushes to the right, and it also pushes up. In part B, when we calculate the tension in the cord, we'll see that that hinge had to have been pushing up. Okay, part B. Calculate the reading on the spring scale. And so the reading on the spring scale is going to be the tension in the rope. So looking at this rod is not rotating. So if it's not rotating, this means that the clockwise torques are going to equal the counterclockwise torques. The net torque is 0 if it's not rotating. We can calculate this weight of this block. I calculated it above. It was 4.9 newtons. The weight of the rod was 19.6 newtons. So the clockwise torque is going to be the torque due to the weight of the rod, and it's going to be the torque due to the weight of the block. The torque due to the weight of the rod is going to be 19.6 newtons times its distance, which is 0.3 meters. The weight of the rod is acting halfway down the rod. And then the torque due to the weight of the block is 4.9 newtons times the full length of the rod, which is 0.6 meters. Again, our point of rotation is right here at this hinge, and so torque is R times the perpendicular component of the force. Well, all of the force is perpendicular to the R vector, and so it's R is how far from the axis of rotation the force is being applied. The counterclockwise torque is going to be due to the tension in the rope. The tension in the rope is applied a distance of 0.6 meters. And if I look back at my original drawing, the tension in the rope can be broken into horizontal and vertical components. And so I only want the perpendicular component of that tension. So that's Ty in that drawing. You don't want to label that in your drawing in A. They don't want to have that extra information there. So go and either work it off to the side or use the original drawing, or you are going to have the test booklet where you're going to write your answers, and then you have another copy of it where, that way you don't have to keep flipping back and forth between pages. And so you can do your sketches in there, but they don't want you to draw components of vectors in part A. In fact, it's not in these directions, but they now specifically say draw the full force itself, do not draw components of the vectors. So if I go through and I solve this for Ty, I get that Ty is 14.7 newtons. And once I have that, I can calculate T. T is the full tension. Ty is opposite the 30-degree angle. So the sine of 30 degrees equals 14.7 over T. So the tension is 29.4 newtons. Okay, now briefly before I go on to part C, I had said that I was going to, in part B, explain why the hinge had to be pushing up on the rod. If we look at this, the Y component of the tension is 14.7 newtons. The total downward force acting on the rod is greater than that. The total downward force is 24.5 newtons. And so that means that on this rod, since it's not moving up or down at all, the total upward forces have to add up to equal the total downward forces. If there's 24.5 newtons acting downward, but there was only 14.7 newtons acting upwards due to the rope, that means that the additional 9.8 newtons had to be acting up due to the hinge. And so you need to make sure that your vertical forces add up to equal 0. Also, your horizontal forces have to add up to equal 0 since it's not moving right or left at all. And so that's why the hinge has to be pushing to the right on the rod, and it's because the tension in the cord pulls to the left on the rod. So those two have to cancel each other out. Part C. The rotational inertia of a rod about its center is 1/12 ml squared, where m is the mass of the rod and L is its length. Calculate the rotational inertia of the rod block system about the hinge. So, first of all, the total rotational inertia is going to be the rotational inertia of the rod plus the rotational inertia of the block that's hanging off the end. An important thing is they tell you the rotational inertia of the rod about its center. If you want to find the rotational inertia of the rod about the hinge, you have to use the parallel axis theorem, or you need to know what it is. If you're going to use the 1/12 ml squared, you use that with the parallel axis theorem, or you need to understand how to integrate to get the rotational inertia. I'll do that separately after I solve this problem. The rotational inertia of the rod is going to equal the rotational inertia of the rod about its center of mass plus the parallel axis theorem says that you add m times d squared, where m is the total mass of the rod and d is the distance from the center of mass of the rod to the axis that this is rotating around. What you're doing is you're looking at the rotational inertia around the center of mass, and then you treat all of the mass as if it was concentrated at the center of mass. You just lump it all into one blob at the center of mass, and the rotational inertia of just a single point-sized object is mr squared, where r is the distance from the object to the axis of rotation. So doing that, we have 1/12 ml squared plus m, and the distance from the center of mass of the rod to the axis of rotation is half of the length of the rod. So adding those together, I have 1/12 ml squared plus ml squared over 4. You need to make sure that you square the numerator and the denominator, which 1/4 becomes 3/12 if I wanted to get a common denominator. So then 1/12 plus 3/12 is 4/12. And 4 divided by 12 is 1/3. So that's the 1/3 ml squared of the rod about its end, which is a common result. It was acceptable if you just knew that result and you used it. They gave full credit for that. but they did give you enough information to be able to get that. The rotational inertia of the block is just a point. So the block just has all of its mass at the end of the rod. So it's going to be m times the length of the rod squared. It's just mr squared for a point mass. So it's going to be mr squared. This m is a different m, it's the mass of the block. And r was the length of the rod, so that's the mass of the block times L squared. And so putting those things together, the total rotational inertia is 1/3 times the mass of the rod, 2 kilograms, times the length of the rod, 0.6 meters squared, plus the mass of the block, 0.5 kilograms, times the distance from the axis of rotation, 0.6 meters squared. And that gives a rotational inertia of 0.42 kilogram meters squared. Part D. If the cord that supports the rod is cut near the end of the rod, calculate the initial angular acceleration of the rod block system about the hinge. So here's our hinge. We still have this weight of 19.6 newtons. We still have this weight of 4.9 newtons. But we don't have that counterclockwise torque anymore. We still have a clockwise torque of 19.6 times 0.3 plus 4.9 times 0.6, which was 8.82 Newton meters. Again, we had that already in part B. That was this. We used that to go through and solve for Ty. So we calculated that. That gave us 8.82. So we're just using that result. But now there's nothing canceling that torque out. So the angular acceleration is the net torque divided by the rotational inertia. So it's 8.82 Newton meters divided by the rotational inertia that we just calculated of 0.42 kilogram meters squared, which gives 21 radians per second squared. And that was the end of the problem. That was a fairly short problem, fairly quick problem. Going through their scoring guidelines, things that they were looking for. In part A, it was worth 4 points. It was 1 point for correctly drawing and labeling the tension. And here they said, or its components, but they have changed their scoring guidelines. They will not give credit for the components. They have specifically asked teachers to instruct students, and the instructions will specifically say in these drawings of the forces to only draw the forces themselves, to not draw any components. And then it was 1 point for correctly drawing and labeling the weight of the rod. And then there was 1 point for correctly drawing and labeling the weight of the block. And then it was 1 point for correctly drawing and labeling the force exerted on the rod by its hinge. Again, it says or its components, not anymore. And so you needed to have the force drawn correctly. It needed to have an understandable label, just saying G is not okay. Just saying gravity is not okay. It could be force of gravity. That would be okay. But just saying gravity is not correct. That's not clear that you understand that it's the force of gravity and not just 9.8 meters per second squared, which sometimes people use that term. They'll say gravity to mean G. And so it was a point for each of the forces, but they had to be correctly labeled, correctly drawn, starting at the correct location. And then one of those earned points was deducted if one or more of the following was present. If there was a correct vector that was not starting on the object, or if the component of the total force was also shown. So if you drew what the net force was also, besides drawing those, or if you drew some other extra vector. So any vectors besides those four would result in a 1-point deduction from however many points you earned. Part B, the tension in the cord. So again, the reading on the spring scale is the tension in the cord. So it was 1 point for recognizing and either saying that the net torque is 0 or somehow showing that in an equation. Somehow your equation should be clear that you realize that you're saying that the net torque is 0 or the clockwise torque equals the counterclockwise torque. Those would both be ways of saying that same thing. And then it was a point for the correct expression for the torque exerted by the cord. So that was Ty times the length of the rod. And then it was 1 point for a correct expression for the torque due to the weight of the rod and the torque due to the weight on the hanging block. So that was the weight of the rod times half the length plus the weight of the hanging block times the full length of the rod. That was the clockwise torque that we had. And then the last point was for solving it. So I said the simplest method is to take the torque about the hinge, directly yielding an equation that could be solved for T. If the torque is taken about some other point, it must be combined with an equilibrium condition. Because this is not rotating, you can pick any point to be your axis of rotation because it's not rotating around that axis. And so the torque around that axis would have to be 0. This way was the easiest way. And so you would go through and you would solve and you get the 29, we got 29.4 newtons. So it was 1 point for this only if you could only get that if you had gotten the previous 3 points. Part C, finding the rotational inertia. It was 1 point for showing or explaining that the rotational inertia was going to be the rotational inertia of the rod plus the rotational inertia of the block. If you had no idea how to calculate that, but you realized that you had to find those two rotational inertias and add those together, write that down. Write down that I total equals I rod plus I block. That would give you one of those 3 points. And then it was 1 point for correctly calculating the rotational inertia of the rod. So that was using the parallel axis theorem, where they said if you simply state that the rod about its end is 1/3 ml squared, that was perfectly okay. And then it was 1 point for the correct expression for the rotational inertia of the hanging block, which was the ml squared. And then you go through and you plug in the numbers and you calculate your final answer. But you could have gotten the full 3 points even if you didn't go through and finish your calculation. If you showed each of those things, that was full credit. You wanted that final answer, though, to be able to answer part D. And part D, this is not an equilibrium, so the net torque equals the rotational inertia times the angular acceleration. So it was 1 point for saying that. or implying it with your formula. It was 1 point for correctly calculating the rotational under, it was 1 point for correctly calculating the torque due to the two weights. So that was the 8.82 newtons that we had on the previous slide. And then it was 1 point for going through and solving for A, or solving for alpha. So for substituting in the rotational inertia that you had calculated, you go through and get this, and we get our answer of 21 radians per second squared. And then finally, they sometimes do have this. There was 1 point for correct units on all of your answers. If you didn't answer a part, you could still get full credit for the unit points if you had units on all of your answers that should have had units. If you didn't answer any of the parts of the problem that were the numerical parts, then you could not get this unit point. So you should put the units there. They don't always have a point for units, but you want to make sure that you have them there so that you don't lose a point for not having the units. Okay. And so the commentary from the head grader. This question was intended to assess students' ability to analyze forces and torques acting on an object with a continuous mass distribution. Part A asks students to draw and label the free body diagram in which forces and their points of application were shown. Usually at least one of the free response problems is going to ask you to draw a free body diagram, a drawing of the forces acting on an object. Part B, they had to calculate the reading in the spring scale. Part C, you were asked to find the rotational inertia. And in Part D, the cord was cut and you had to find the angular acceleration. How well did students perform? The average score was a 6.51. That was actually fairly low. Again, I said that if you understand rotation pretty well, you should easily get 10 or more points on this. And if you did, you would be ahead of the national average, and that's ultimately what you want to be. If you want to be in that 4 or 5 range, you definitely want to be above the national average on the majority of things. 15% of students earn scores of 12 or higher, and about 28% of students earn scores of 3 or below, which I would actually say is a very large percentage for this problem. It should not have been that difficult. There are 3 points right there for drawing the forces, and you should have been able to get more than that. What were common student errors or omissions? In Part A, most students were able to construct at least 3 of the forces in the free body diagram, but most students omitted the force exerted by the hinge on the object. Some students might have misinterpreted a frictionless hinge to mean that there were no forces due to the hinge, but that would not be true. In Part B, many students summed the forces rather than the torques. Again, that was something that I saw in grading the problem. It's not that the y component of the tension equals the vertical components of the weight. It's the torques that add up to equal 0. There were some other people that said that the tension equaled the 2 downward weights added together. Those would not be correct. So among those students who did utilize torque, many did not correctly treat the torque on the rod due to the string. So that was by finding the y component of that tension and solving for that. Most of these students were able to correctly sum the torques due to the weight of the hanging object and the rod itself. So you definitely should have been able to do that. You should know how to go through and do the rest of it though. In Part C, many students understood the parallel axis theorem was needed, but were unable to apply it correctly. That's something that I find is that people don't use the parallel axis theorem correctly. There's not much that we did with it in class, but it's because there's not much to it. There aren't a whole lot of problems that we can do with it. You just have to practice using it, and you have to understand how to use it. But it's one of those that, it doesn't come up in, millions and millions of problems. There's not a lot to do. It's just knowing how to use it. Some students use the parallel axis theorem for the bar, but forgot to include the rotational inertia of the attached block. So some people just did 1/3 ml squared, and that was their final answer. And many students failed to substitute correct distances for the bar and the block. And then in part D, many students used only the torque by the hanging mass instead of looking at the torque applied the weight of the bar also. So there are suggestions. Based on your experience of student responses, what message would you like to send to teachers and to their students? So regarding free body diagrams, students should represent each force in one of two ways, either the vector or its components, but not both. And in fact, it was after this year, after the test that was given this year or maybe the following year, that they changed their rules where they did not want people to give it in terms of its components at all. So students should represent each force only with the vector and its direction, but not with the components. Okay, again, it's because when they're grading these, it's hard for them to tell whether you mean for the vector and its components to be two separate forces or not. So they have eliminated that. They only want the full vector itself. They don't want you to draw any components of vectors at all. It says students should include an arrowhead on any line intended to represent a vector. So you have to have the tip on the vector. Students should label forces correctly, either W or mg for weight, not g. Students should make sure that that one end of each vector is drawn touching the object. Students should avoid drawing any extraneous vectors which could reduce a student's score on a problem. Each force vector drawn should represent a single force, not the net force or some other combination of forces. For example, in this problem, students should have drawn a vector for the weight of the bar and a separate vector for the weight of the attached block. And if a free body diagram, with components drawn in is needed to solve any successive part, you should not put these things in your original free body diagram. You should instead draw another diagram. That's why I said draw your forces on the original drawing that they gave you instead of on the space for part A, or draw them on your sample test copy, the one that you're not turning in, rather than in your test booklet. You don't want to have those components drawn. The components are very important. They help you solving it, but you should not have them in your drawing in part A. You should have them in a separate drawing off to the side. They also said that students should have more experience with applying the parallel axis theorem and having rotational inertia of several objects. In the homework, I am giving you several problems where you have rotational inertia of several objects put together. That's because you need this practice. And again, for that unit point, they say that teachers should continue to emphasize the importance of using correct units. So you need to put units on all of your answers. You might not lose any points because of it, but you might lose a final units point, and every point helps. Okay, just quickly, I want to go through integrating to find the rotational inertia of the rod about its center, and getting 1/12 ml squared, or integrating to get the rod about its end. If we're looking at the rod about its center, this is a rod of length L and a mass M. For a continuous object, you break it up into little pieces dm. And the rotational inertia of just that piece is r squared dm. And then you have to add up all of the pieces. That's what the integral is. So for this, x is going to be my distance from the axis of rotation. So for this problem, I have the integral of x squared dm. But I have a problem there. X is my variable, but it's saying integrate with respect to m, and so I need to get dm in terms of x. The total mass over the total length of the bar equals the mass of just the little piece dm over the length of the little piece dx. So dx is just the width of this little piece here. So that ratio has to be true. Again, if you can find the mass per length and you multiply by the length of your little piece, that gives you the mass of that little piece. So this gives me that the rotational inertia is m over L. Those are constants, so I can pull them out in front of the integral. And it's the integral of x squared dx. But the important thing is x is negative L over 2 on the left-hand side, and x equals positive L over 2 on the right-hand side. So I'm going to integrate from negative L over 2 to positive L over 2. The integral of x squared dx is x cubed over 3. So this is m over L times the quantity x cubed over 3, evaluated from negative L over 2 to positive L over 2. So that's m over L, and this is L cubed over 8 divided by 3 minus negative L cubed over 8. Again, when you cube a negative number, it's still negative, divided by 3. So that's m over L, and this is L cubed over 24 minus negative L cubed over 24. Which is m over L times L cubed over 24 minus negative L cubed over 24 is L cubed over 24 plus L cubed over 24. So 2 over 24 is 1/12. L cubed So one of the L's divides out, and you have 1/12 ml squared. If you wanted to do the rod about its end, the only difference is x equals 0 is going to be at the one end of the rod, and x equals L is going to be at the other end of the rod. X is your distance to this end of the rod. So you're, instead of integrating from negative L over 2 to L over 2, you're going to integrate from 0 to L. But it's going to be the exact same function. You're going to be integrating x squared dx with m over L out front. All of that setup is going to be the same. So I is going to be m over L times the integral from 0 to L of x cubed dx. So this is m over L times L cubed over 3 evaluated from 0, x cubed over 3 evaluated from 0 to L. Which is m over L times L cubed over 3. And again, one of the L's divides out, and we get 1/3 ml squared. And in fact, this could be done for finding the rotational inertia about any point on the rod. If I wanted to put my axis of rotation a third of the way down. So it's not about its center, it's not about its end, it's going about this point that's a third of the way down. Then I'm just going to have one limit as negative 1/3 L, and the other end is going to be positive 2/3 L. And so my rotational inertia about this new point is going to be m over L times the integral from negative L over 3 to 2L over 3 of x squared dx. So looking back up, I copied something down incorrectly. This should have been x squared. I did the integral in my head, so I combined too many steps there. I apologize for that. So this should be x, the integral of x squared dx. So the only difference is this is m over L times x cubed over 3, evaluated from negative L over 3 to 2L over 3. So it's going to be m over L times 2L over 3 cubed is going to be 8L cubed over 27 divided by 3 minus negative L cubed over 27 divided by 3. So that gives m over L. 8 over 27 divided by 3 is 8 over 81. So this is 8L cubed over 81. Minus a minus becomes plus. So it's plus L cubed over 81. So this is m over L times 9L cubed over 81. Which that gives 1/9. So this is going to be 1/9 ml squared. Again, finding the rod about any point along the rod, you could go through and you could do this integration and it just changes your limits of integration. Or if you know the rotational inertia about the center, the 1/12 ml squared, then finding any of these other rotational inertias is just using the parallel axis theorem. So any of those ways are proper ways of doing this. Again, you should know how to do a rod about any point on the rod. They do ask people to do that. It's not uncommon for them to ask that, but that's really the only one that they usually ask. Again, rotation is definitely one of the things that you want to practice. If you practice all of the rotation stuff, if you look at it, those sometimes are the trickiest problems for people on the free response part. And if you can do those well, you're setting yourself up to get a very good score on the AP test. Keep studying.